Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're evaluating beam deflections using moment area methods. Our lesson objectives are to evaluate beam deflection and/or rotation at points of interest through appropriate application of the moment area theorems. The first one, which says that the difference of the rotation between 2 points is equal to the area of the bending moment diagram between those 2 points divided by EI. The second moment area theorem, which says T at B with respect to A equals x bar, it's a centroidal distance, times the area of the moment diagram between A and B. A little more explanation is required on how to use that second moment area theorem, and we'll see examples in the upcoming videos. Our first example is a cantilever beam with a distributed load over the end. We're asked to evaluate deflection and rotation at the free end of the cantilever beam. Let me sketch the deflected shape real quick from end A, no rotation, and then the distributed load at the end will cause the beam to bend downward. The deflection at the end, I'll label delta B, that's one thing we want to find. Our rotation at the end, that's this rotation with respect to the horizontal, it's called theta B. That's another thing that we want to find. The first moment area theorem says that the rotation between 2 points is equal to the area of the bending moment diagram. This theorem is useful if I know the rotation at any other point on the beam, and I do, in this case, know that the rotation at end A is 0 because of the fixed support. So theta B minus theta A, in this case theta A is 0, is equal to the area of the bending moment diagram from A to B, which in this case is the whole beam, and then divided by EI. That's how I'll apply the first moment area theorem to solve for rotation. So now I need a bending moment diagram. Start out with beam reactions. A sub y balances the applied force, 2 kips per feet times 6, which is 12 kips. This force also causes a moment in the clockwise direction about A. It's going to be balanced by a reaction in the counterclockwise direction. That reaction has a value of the total distributed point of action of the distributed load. The distributed load has a total force of 12 kips, and the point of action halfway between there is 8 plus 3, 11 feet, and that equals 132 kip feet. So that's our moment at the left end, 132 kip feet. Let's work by drawing the shear force diagram. Shear force in kips jumps up to 12 kips and then decreases linearly back to 0. This value here is 12. 12 minus 2 times 6 does come back to 0, so that one looks good. Draw my moment diagram. I'm going to leave a little bit of extra room here. Make sure I have my lines extending downward. Okay, my moment in kip feet. Moment is going to drop to negative 132. And then it's going to increase linearly where shear is positive. And 132 plus the area of the shear diagram, 12 times 8, which is 96. Negative 132 plus 96 is negative 36. And moment is negative. And then finally, negative 36 plus 1/2 times 12 times 6 is equal to 0. And its moment diagram is quadratic in that region. Okay, so now we just need to find the total area of this bending moment diagram. I'm going to break it into 2 separate areas, A1 and A2. A1 being the linear portion and A2 being the quadratic portion. Okay, A1, we can find the area of the trapezoid. We've done this many times. 1/2 times negative 132 minus 36 times the distance between those points, 8 feet. Okay, this is the average value, average height times 8 feet, and that equals negative 672 kip feet squared would be the units. Area 2. Now it turns out that the area of a quadratic region is equal to 1/3 of the total area under the enclosed rectangle. So 1/3 times base times height. That we can calculate as 1/3 negative 36 times 6, which is the length of that region, and that is negative 72, also kip feet squared. So now theta B is equal to A1 plus A2. We'll just add the areas together over EI equals negative 672 minus 72 kip feet squared divided by EI, which is given as 500,000 kip feet squared. Those units cancel, which is good because theta B should be unitless. It's a rotation, and actually the units are radians, negative 0.0015 radians. Okay, now the second part, we want to find the deflection at the end. I'm going to go to a new page here and summarize what we need to know to do this. Here's our moment diagram from before, deflected shape of the beam, and delta B. And I claim here that delta B is equal to T sub B with respect to A. So let me explain a little bit more about what this means. T sub B with respect to A is the distance from the deflected shape of the beam at B to a tangent line drawn from point A to point B. And that tangent line should be tangent to the deflected, have the same slope as the deflected shape of the beam at point A from where it's drawn. So if I draw a tangent from point A that's tangent to the deflected shape, that tangent line is a horizontal line for this particular case because the slope of the beam, or the slope of the deflection, is 0 at A. So therefore, T sub B with respect to A is the distance from the tangent line, which is the horizontal line, down to the deflected shape, and that's equal to the deflection. So this is almost always true for a cantilever beam. That moment, the second moment area theorem, is very easy to apply because the delta B is equal to T sub B with respect to A. That's generally not going to be true for simply supported beams and beams with overhangs and so on, only for cantilever beams. So they're kind of the easiest example and a good one to start with. Now let's focus on evaluating this T at B with respect to A. Basically, we need to sum the x bar, and x bar is the distance from point B to the centroid of the area. X bar equals distance from B to centroid of the area, and then you're going to multiply that times the area. Now for this particular moment diagram, it's very difficult to evaluate a centroid of the whole area, so again we have to break it down into regions. And in fact, we can't even easily evaluate the centroid of a trapezoidal region. Maybe we can, maybe it is possible to do so, but I'm simply going to use an intuitive approach and break it down into a rectangle and a triangle. Okay, so I have three regions now with which to evaluate. I'm going to call this one here A1, A2, and this final one over here A3. Okay, so I'll need to evaluate the area of those three regions separately. I'll need to identify the centroid of each region. I'll approximately locate the centroid visually, and then evaluate the x bar distances. Okay, remember since T at B with respect to A, our centroidal distances are evaluated with respect to B. So x3 is going to look like that. x1 is going to be that distance. And x2, maybe I'll drop this down like that, is going to be that distance. Okay? Starting with x1. x1 is equal to the 6 feet on the end plus 2/3 of the way over the triangle, so 2/3 times 8, 2/3 times that length, and that turns out to be 11.33 feet. Okay, x2 is equal to, again, the 6 feet over the distributed load portion plus half of the 8 feet, so 6 plus 4, or 10 feet. And finally, for a quadratic shaped area, the centroidal distance is located 3/4 of the way from the small end, 1/4 from the big end. You need to know which one it is. Here we want from the small end, so 3/4 times 6, or 4.5 feet. Okay, and we have some rules summarized in the notes for you to be able to remember how to evaluate these areas and centroidal distances. Okay, so finally I can do this by adding together the x-bars and areas for each region. So x1 times a1 plus x2 times a2 plus x3 times a3, and then divide by EI. Okay, starting with x1, 11.33 feet. Area 1 is the area of this triangle. I'm going to note that that height, 132 minus 36, is equal to 96. So the area of the triangle, 1/2 times 96 times 8. Okay, so that's x1, and that's a1. And the units here for this guy should be feet squared. Okay, and then I'm going to, and notice that all of these are negative. All of the areas times x-bars are negative because the bending moment diagram is negative. Next, x2, 10 feet, times a2 is the area of this rectangle, 36 times 8, and get feet squared. That's x2. Sorry, this should be a plus because I'm adding all these together. x2, and this is a2. And then plus a negative for region 3, x bar, 4.5 feet, that's x3, times the area. We calculated this area just a bit ago, and that area was 72 feet squared for a3. Okay, so that whole thing, I'm running out of room here, I apologize. When we add all those numbers together, it equals negative 75 54.7 kip feet cubed, and then I'm going to divide it by EI, which is 500,000 kip feet squared, and the number computes to a negative 0.015 feet. Okay, so that is my answer. Delta B, summing all those x bar times area together, is equal to negative 0.015 feet, or about 0.18 inches. Fairly small deflection for this beam, which seems reasonable. And that concludes this video.